I decided to switch up the location of the doc cam and the. I guess that's off, but you can see this. I decided to switch up the doc cam and the slides because I always turn to the wrong one. So see if this is going to help me. I feel like I always turn to the wrong screen when I'm expecting the notes. Today we have on the books to do duality, uses, and correspondences. We didn't quite finish up the lecture on KKT conditions. I really think we could do either, so it's just dependent on the class's interests. The bit we learned on uniqueness and L1 penalized problems, that's not going to play a major role on the homework, say, or on the midterm. So as far as knowing, the minute details of why this result is true is not crucial. But it is a nice example of a use of the KKT conditions. So I guess I could go either way. Maybe we can just take a vote. How many people want to continue going through the proof of this result? And how many people want to actually just move ahead to our kind of duality uses lecture? Let's hear how many people want to hear the proof of that result in detail. Raise your hands high. OK, and how many people want to move on? All right, I guess it's a pretty clear consensus. You guys all fail, by the way. You all get Fs. No, that's fine. Totally fine. So let's move on to duality uses and correspondences today. You can just have in the back of your mind that if you're solving an L1 penalized problem, that you often have a unique solution, even if you have more variables than, say, observations. So this is going to be our last lecture in the unit on duality and optimality. On Thursday, the plan is to go ahead with Newton's method, which is going to start with our second unit on algorithms. So today we'll try to kind of finalize all of the various perspectives we've seen so far on the KKT conditions and duality and give some use cases of duality. And people have had questions about this kind of throughout our lectures on duality, so hopefully this will provide some answers. All right, so last time we talked about the KKT conditions. Just to remind you, the idea is you have a problem of this form, general optimization problem. We wrote down a list of 4 conditions, essentially, that were called the Krush-Kuhn-Tucker conditions, or the KKT conditions. And they were as follows. They're a set of conditions that apply to a point x and to a pair of points u and v, where x is the primal variable for this problem, and u and v were dual variables for the dual of this problem. The first condition is called stationarity, and it says that if I were to form the Lagrangian, and I were to look at the minimum of the Lagrangian over all x, then x must be a minimizer, because the subgradient of the Lagrangian with respect to x with u and v fixed at their values must contain 0, or must be 0. The second condition is called complementary slackness, and it says that either the dual variable that I have corresponding to each inequality constraint ui, or the achieved value of the inequality constrained function, hi of x, must be 0. One of the two must be 0 for every I. That's called complementary slackness. And the last 2 conditions are just that the variables we're looking at must be feasible for their respective problems. X must satisfy all the primal constraints, and u and v must satisfy all the dual constraints. And what we learned last time is that these are always necessary for optimality. No, excuse me, I said that wrong. They're always sufficient for optimality. So if I ever give you a pair of points, a triplet of points x, u, v that satisfy the KKT conditions, then they imply that you have the optimal primal and dual solutions. So they're always sufficient. We proved that. And we saw that they are necessary under strong duality. So if the primal and dual problems here had optimal criteria values that matched, which we call strong duality, that implies the KKT conditions must hold. Okay, so we saw that, for example, if we had convex problems, if we had a convex primal that was strictly feasible, then we know that strong duality holds, something we learned when we talked about Slater's condition. And under that kind of regime, the KKT conditions are necessary and sufficient for optimality. So they completely characterize the set of solutions you have in your primal problem and the dual problem. Any questions about that before we move on? That was our last lecture. Okay, so today we're going to, oh yeah, Christoph.
So the first condition, stationary condition, is basically the subdifferential. Like 0 is the subgradient of the Lagrangian. Does this like sum rule for the subdifferential always hold, or for non-convex functions?
The sum of functions?
The sum rule that the
yeah.
sum of two, that the subdifferential of the sum of two functions is the subdifferential of each of those?
Yes, yeah. I think that just holds right from the definition. Yeah. Right, so that also brings up another point which is important just to mention. We talked about this last time, which is that they're always sufficient for optimality. So if you could find a triplet of points that satisfy these, you have yourself primal and dual solutions. So you can, be happy. But there's something subtle here, which is that if you have a non-convex problem, then it could be very hard to satisfy the stationarity condition. Because in particular, we may not know how to take this. We may not know what subgradients of our functions are. Right? Subgradients correspond with gradients in the case of smooth convex functions. But for smooth non-convex functions, they need not. Okay, so while these are always sufficient, they may be very hard to work with for non-convex problems. So thanks for reminding me of that. Okay, two uses of duality. These are things that we, I think, discussed somewhat in passing from the last couple of lectures, but these are going to be something that we think about in detail today. Actually, the first one we'll kind of return to when we talk about algorithms, but we're going to at least mention it. If you have a primal feasible point x and dual feasible points u and v, then we call the difference in primal and dual criteria, so f of x minus g u v, the duality gap between x and uv. Okay, it's just the difference in the achieved primal criterion value and the achieved dual criterion value. Now, the first thing we know that this is always non-negative, right? Because if I have any primal feasible point and any dual feasible points, then I must have f of x bigger than or equal to g of uv by construction of the dual. But more importantly, this is actually an upper bound. This non-negative number is an upper bound on how far I am from optimal. Okay, for example, it's an upper bound on the difference between f of x and f of x star. Right? Why is that true? It's true for a very simple reason. The duality gap, we just observed that f of x star is always bigger than or equal to g of uv for any dual feasible u and v, right, by construction of the dual. And therefore, if I look at the distance between, or if I look at the amount suboptimal I am, f of x minus f of x star, this is always less than or equal to f of x minus g u v. And likewise, if I look at, let's call it g of u star v star minus g u v. Okay, this is always less than or equal to f of x minus g u v. Okay? So what that implies is that this quantity here, which is computable, right? Suppose I was running an algorithm on the primal and the dual at the same time, and I just stopped at some point, and I took the uv I found and the x I found. That gives me a very rigorous upper bound on how far I am from optimal for both the primal and the dual problems. So if I stopped when my iterates, my primal, my dual iterates were, say, had a duality gap that was 0.01, I know that I am at most 0.01 away from optimal for both the primal and the dual problems. Very, very useful as a stopping criterion. Okay, so the duality gap is a very practical quantity algorithmically, and we'll return to that when we talk about algorithms. For example, the second order methods unit is going to use this fact when we talk about interior point methods. It's going to be very useful. Okay, so that's maybe our first rigorous form of a stopping criterion we've seen so far in this class. The other ones we've been kind of vague about it. One very nice use of duality. Another nice use of duality is the following, which comes really right from the stationarity condition. So it's been in front of us for a couple lectures, but we haven't maybe announced it, which is that under strong duality, if I tell you that the KKT conditions must hold, and you tell me you've computed a dual optimal pair U star and V star, then I know that X star must minimize the Lagrangian once I stick in U star and V star. That's the stationarity condition, right? If I tell you that I have a dual optimal solution and I have strong duality, okay, so if you derived the dual, you solved it, got a dual solution U star V star, and you knew that strong duality held, maybe say because the primal problem was convex and strictly feasible, then you could get a primal solution by invoking the stationarity condition. So in other words, from stationarity, we know that X star minimizes the Lagrangian over all X evaluated at U star and V star. Okay, so often we're going to see this actually characterizes our primal solution. So if you happen to solve the dual, you could get a primal solution out of it. And that's favorable when the dual problem is easier to solve than the primal. Okay, so another very important use of duality. So let's be a little more explicit about this. Let's say a little bit more. If we had an optimal dual solution U star V star, then the stationarity condition tells us, under strong duality, that any primal solution must solve this problem. Minimize over all x, f of x plus the sum of ui star hi of x plus the sum of, I guess I should say, vj star lj of x. Okay, so oftentimes, if we're lucky, solutions of this unconstrained problem can be expressed explicitly. I can actually write down an explicit form for x as a function of uv star, and that gives us an explicit characterization of primal solutions from dual solutions. If, in addition, the solution to this problem is unique, which happens when, suppose, f of x is strictly convex, then I have an explicit unique solution for the primal given a dual pair, U star V star. Okay, so and as we said, this can be very helpful to solve when the dual is easier than the primal. And we're going to maybe remind ourselves when that's going to happen just through the examples we go through in this lecture. So let's pause for questions just for a second before we proceed with examples. Yeah?
Since each value of u is constrained to be positive, or does that impact our ability to solve this?
No, so remember that u and v are considered fixed here. There's no minimization over u and v. So we're supposing that we've derived the dual, like we wrote down on paper. We went and solved it with an algorithm. And then we said, well, I didn't really want to solve the dual. I want to solve the primal. And we're asking how to recover the primal solution. So we're just writing down another problem which characterizes the primal in terms of u and v. Other questions? OK, so here's an example, a very simple example from the textbook for this course, the Boyd and Vandenberg textbook. Let's suppose this is our problem. We want to minimize the sum of fi of xi subject to A transpose x equals b. And each of these fi's are smooth, strictly convex functions. Okay, they can be complicated, but just for the purposes of this example, let's suppose that they're differentiable and they're strictly convex. Now this is almost a very nice problem. So here you could think of each xi as univariate, which is what I've done in the slides. So xi is just the ith component of x. You could also think of maybe xi as a block of variables. The same kind of arguments would hold in this case. This is almost a very nice problem, except for this complicating equality constraint. Okay, so we can't exactly separate this into n separate minimization problems because of this equality constraint, which ties them all together. Right? So we could, if there wasn't this equality constraint, we could minimize each fi of xi separately without this inequality constraint, which may be a lot easier or a lot more efficient. We could maybe do it in parallel, trivially in parallel. But this is a complicating equality constraint which ties all of our primal variables together, and it makes this problem harder. Okay, so this is going to be a hint at what's called dual decomposition, which is something we'll return to when we talk about advanced methods at the end of the semester. But we can just see here, derived from the dual, how things get easier. So let's write down the dual function. just from the definition. I'm going to only define one dual variable. So my dual problem is going to have one variable because I have one constraint here. Right? So v is the variable I define with respect to this equality constraint. And there's no constraint on the sign of v since it's an equality constraint. And so g of v is going to be given by the minimum over all x of the Lagrangian, which is fi of xi, the sum, plus v times b minus a transpose x. And I can write this, the Lagrangian, right, is a function of x and v. I can actually write this as the sum from I equals 1 to n of fi of xi plus ai transpose, actually ai xi, rather, times v with a minus sign, and I have a plus bv. Okay? And now my task is, my task is to minimize this over all x to form the dual function. But look, with respect to the Lagrangian, because there's no constraint, that's quite easy. This separates out into n separate minimization problems. So all I've done is I've written out the inner product of A transpose x as the sum of ai xi, and I've wrapped it into this sum. So to minimize the Lagrangian over all x, I can actually perform n separate minimization problems, each one over xi. And this is going to define my Lagrange dual function g of v. Right? This is what we call g of v. Now we're going to see just in a few minutes that this is a special case of what we call the convex conjugate of fi. Okay? It's actually the negative convex conjugate of fi. But you could think about in this example, if fi was smooth and convex, then you might just differentiate this and set it equal to 0 and figure out, right, which value of xi achieved the min here. So this might be a very easy problem for you to do because it's a smooth convex function in one variable. So let's just denote this minimum for the meantime by we're going to denote this by negative f star I of aiv. And we're going to learn exactly what the convex conjugate is in just a few slides. But like I said, you could think about just deriving this based on first principles from the fact that fi is smooth and convex. And once I've done so, here's my dual function, right? I just take the bv I had, I add up all of these over across all I, and that's what I have. My dual is just bv minus the sum of the convex conjugates of fi evaluated at aivi. And now look at this dual. It's a problem in one variable. Okay, so the dual here is much easier than the primal in the sense that it's a one-dimensional minimization problem. So you could do whatever you want. I mean, I would claim that even non-convex one-dimensional minimization problems are easy to solve. I guess we never explicitly discussed this, but how would you solve a one-dimensional minimization problem? What would you do? Say before you took this class, how would you solve a one-dimensional minimization problem?
Bisection method.
Okay, bisection, but how about just grid search, right? Lay down as many grid points as you can afford and just check all the values of the function. Bisection is, of course, more clever. Maybe it's more proper, but even for a non-convex function, a one-dimensional minimization is not hard. Just do a grid search, right? And if it looks like you haven't found the solution, then just expand the grid. So there are many ways to solve a one-dimensional minimization problem. And however you do it, bisection method, there's some methods based on golden search or whatever, some fancy ones, or just a very simple grid search. Try a bunch of trial values. You could solve that dual pretty easily. And then we can recover the primal solution because we know that if once I have the dual solution v star, the primal solution solves the following expression. It must minimize the Lagrangian, right? If you go back to the Lagrangian, the primal solution must minimize this once I stick in v star over all x And actually, that characterizes each component xi individually, because it separates out. And it says that if I could solve this equation, right, I'm trying to figure out which value of xi minimizes each of these terms, given the optimal value of v. If I could solve this equation, which this gradient equation, right, gradient of fi of xi equals ai times v star for each I, then I have the primal solution. That's all I have to do. Okay, so it's a way to get the primal solution in terms of the dual. The reason I've been able to take a gradient here is that I've assumed that each fi is smooth and convex, so the minimizer of each of these terms is just given by taking it's actually the derivative and set it equal to 0. So since this is a univariate function, this is actually just the derivative. I could have written fi prime here. Questions about that? Han? So it's a good question. The question is, what happens if I can't compute fi star that I defined here, say? And for this lecture, we're going to assume that we're going to be able to compute it for whatever functions we have in mind. At the end of the course, when we talk about dual decomposition and dual methods, we'll see we can actually still get away with maximizing the dual, even when we don't know the form of the conjugate. So there are methods like dual ascent and the augmented Lagrangian methods that don't require knowledge of the conjugate function and still apply to the dual. But just for today, we're going to pretend like every function we encounter, we can derive its conjugate. Good question. Other questions? OK, here's an outline for today. Let's talk about dual norms, which we've encountered a few times, but just give a more kind of explicit discussion of them. Then we're going to define conjugates. And you'll see that they have a very kind of intimate relationship with duality, and that we can pretty much compute conjugates anytime we can compute dual functions, and vice versa, because they're basically expressing the same quantity. Then we'll talk about dual cones, and lastly, some dual tricks and subtleties. Some tricks to deriving dual problems and some subtleties when you do so. So there are many other uses of duality and relationships that we could discuss. And in previous years, I've kind of gone off on the deep end and talked about various ties to duality in math and in geometry, other ways. So if you're interested in that, you can take a look at the slides from previous years. I think for this year, we're just going to stick to this one lecture. Don't want to exhaust you guys too much with the relationships to duality. But just know that it's a very broad concept. So if you hear the word dual in, say, geometry or dual in mathematics, then they often relate to this kind of dual that we're talking about here. OK, what are dual norms? So we've discussed these a bit already. Let's just first name kind of two canonical examples of norms we've dealt with. We've looked at LP norms, which are given by for some value p bigger than or equal to 1. They're defined by taking the sum of the absolute value of the powers of p of xi, powers of p of the absolute value of xi, summing them up, and then taking the entire sum to the power of 1 over p. So the cases we've studied have been, say, the 2 norm and the 1 norm and the infinity norm, but this is also defined for any p bigger than or equal to 1. It's in fact defined for p smaller than 1 as well. It's just not convex in that case. Okay, it's not really a norm in that case, even though we call something like an LQ norm or something, or an LP norm when p or q is less than 1. That's really a misnomer. It's only a norm when p is bigger than or equal to 1. And the trace norm we've also looked at when we talked about matrix completion. If you give me a matrix X, the trace norm is the sum of its singular values. Okay, so two kind of important norms we've seen so far. For any norm, not just these two, for any norm, we define this dual norm as follows, and we denote it by, if the original norm is just denoted by the usual double bars, the dual norm is denoted by the double bars and then a star. And it's defined to be the maximum of inner products we can take with x, so z transpose x, over all points that have norm less than or equal to 1 in the original norm. That's the definition of the dual norm. So you can check, first of all, that this is indeed a norm. So check all the properties of a norm. You can check this satisfies all the property of a norm. So whenever this original norm was indeed a norm, so will the dual norm be indeed a norm. And you can also check right from the definition that we have something like the Holder inequality, or something like Cauchy-Schwarz for L2, which is that for any points z and x, I have z transpose x is less than or equal to the norm of z times the dual norm of x. Why is that? Well, it comes right from the definition, right? Z transpose x in absolute value, let's just quickly derive that. I have x star being defined to be equal to the max over all z with original norm less than or equal to 1 of z transpose x. And that looks like a dual norm, just supposed to be the norm of z. And now let's plug in a particular example. Right, let's just plug in any point you want. I guess I called it z on the slides. Let's just call it y here. Let me take y over its primal norm, transpose x. Then that's going to be less than or equal to the maximum for any point y whatsoever. And hence, y transpose x is less than or equal to, just rearranging this, right? Less than or equal to the norm of y times the dual norm of x. This entire thing was pretty confusing. Sorry about that. This is supposed to say the dual norm of x. Okay, and the same is going to hold if I just use negative y in here. So I actually have the absolute value of y transpose x is less than or equal to the norm of y times the dual norm of x. So we get back Cauchy-Schwarz for the L2 norm, because you can check, indeed, that the dual of the L2 norm is the L2 norm. And we get back Holder's inequality for all the LP norms, and we have this kind of just more general inequality for any norm and its dual. Okay, so it gives us this nice, useful bound for any pair of norm and dual norm. And if we go back to these specific examples of norms, the LP norm and the trace norm, you could also check, right from the definition of these two, that the dual of, say, the LP norm is the LQ norm, where P and Q satisfy 1 over P plus 1 over Q equals 1. So that, for example, when P is 2, Q must be 2. When P is 1, Q must be infinity. And the dual of the trace norm is indeed the operator norm. So if I were to form this expression, then what I will get out is the maximum singular value, which defines the operator norm. Another important fact is that the dual of the dual norm is indeed the original norm. So that's something that I don't remember if we have on the homework. But if we don't, then you should just practice after this lecture, after we learn conjugates and we go through some examples of dual norms, it's a be good practice to try to prove this right from the definition. It's not hard to show right from the definition. Okay, so that means that, for example, the dual of the operator norm is the trace norm, and the dual of the LQ norm is the LP norm for these examples, right? This goes both ways. All these statements go both ways. Questions about the dual norm? Yeah?
For the definition of the norm of z is smaller or equal to 1. Can I say the norm of z is equal to 1 because I've seen the maximum here she adds the norm of z is equal to 1?
Yes. So I mean, I think. Yeah, I think it's clear that if you constrain the dual norm to be equal to 1, then you'll get the same answer. That's not a convex constraint, so we typically write it like this. I haven't actually seen it written with equality, but it would be the same thing. Other questions? OK. So we're going to see the dual norm relates to the concept of convex conjugates, which themselves relate to duality. So these kind of provide the tie. Conjugates provide the tie between all sorts of different related quantities. And they're defined as follows. If you give me any function which goes from R into R, convex or not, just any function, I can always define its conjugate Sometimes we call that the convex conjugate for a reason that will be clear shortly, as another function that goes from R into R that's defined as follows. F star at y is given by the maximum value I can find over all x of y transpose x minus f of x. So it's the maximum discrepancy between a linear function of x, where the slope is kind of given by y, and the function itself. Maximum of y transpose x minus f of x. So this is a picture for what happens when the function is univariate. The conjugate is defined as the maximum discrepancy between x, y, and f of x itself. The biggest gap I can find between a linear function of x with slope y and f of x. When f is differentiable, this is sometimes called the Legendre transform. So you'll have seen that probably in physics textbooks or in physics classes. And although I haven't put this on the slide, this is what people often call the Fenchel dual of the function f. It's just another word for it. Okay, we're going to call it the conjugate in this class. So what's a very important property? F star is always a convex function, even if f was not convex itself. So if I take the conjugate of any function, I always get f star, which itself is convex. Why is that true? It's true for a very simple reason, which is that it's defined as the pointwise maximum of convex functions in y. Right? If I view this as the pointwise maximum of a bunch of functions in y, each of these functions just being affine functions of y, right? Because the only role y plays here is y transpose x. Then each of these is trivially convex. And so the pointwise max is going to be itself convex as a function of y. Okay, very simple application of some of our rules for convexity. So let's just pause and stare at that for a second. So let's go through a few properties of conjugates before we derive some examples. The first property of conjugates is often called Fenchel's inequality. And it's similar to the dual norm inequality. And in fact, it's kind of derived the same way, essentially, except that it's additive rather than multiplicative. And it says that for any points x and y, x transpose y is upper bound by the value of x under the function and the value of y under its conjugate. So it's less than or equal to f of x plus f star of y. Okay, so let's just derive that right from the first principles. It's a one-line proof. This is defined as the maximum over all x of x transpose y minus f of x. So in particular, it's going to be bigger than or equal to the value that I look at for any one x. Right? And rearranging just gives me that upper bound. So I always have x transpose y as upper bound by f of x plus f star of y. And more so, I get an equality here when x actually is the guy that achieves the max here. So the inequality is called Fenchel's inequality. If we take the conjugate of the conjugate, so f star star, then one can show that that is always a lower bound on the function pointwise. So f star star less than or equal to f. By this I mean that f star star of x is less than or equal to f of x for all points x. So it's a pointwise lower bound on the function. And if f is what's called closed and convex, then f star star is equal to f everywhere. So the conjugate of the conjugate is the original function. Did we discuss what closed meant in this class? Did we talk about that? We haven't talked about that. So a sufficient condition for a function being closed is that it's continuous. So think about it as continuous. It's actually weaker than continuity. It's equivalent to what's called lower semi-continuity. Another definition is that a function is closed if all of its sublevel sets are closed sets. So if I take my function, I look at all of its sublevel sets. If they're all closed, I call the function closed. That happens in particular when f is continuous. So if you have a continuous function, it's closed. It's just that closed is a little bit weaker than continuity. So any function that's continuous and convex has the property that when I take its conjugate twice, I get back the original function itself. Okay, another pretty useful property. It's akin to what we saw for the dual norm, right? The dual of the dual is the prime of the dual of the dual norm is the original norm. This is also true for conjugates, just under kind of somewhat minor conditions on the function itself. Well, convexity is a major condition. Closedness is not. It's a minor condition. If f is closed and convex, then for any points x and y, we actually have a very useful relationship between the subgradients of our conjugate and the subgradients of our original function. And this will be kind of critical importance when we come back to dual methods for the advanced algorithms unit. And that is the following relationship. If you ask me for subgradients of my conjugate function, and I look, for example, I declare that x is a subgradient of my conjugate function at a point y, then that is true if and only if y was a subgradient of the original function at the point x. So as I move from conjugate to my original function, the roles of x and y get reversed. But deriving subgradients, in a sense, is just as hard for the conjugate as it is for the original function because of this implication. Okay, so x is in the subdifferential of f star if and only if y is in the subdifferential of f at x. And these two properties are both equivalent to getting an equality in Fenchel's inequality. Okay, f of x plus f star of y is equal to x transpose y. I honestly can't remember whether they put this in the homework. Dallas, do you remember whether this is on the homework? So another one of these facts that if it's not in the homework, I would definitely go through trying to solve it yourself, because hint, hint, it's not a bad midterm question. Something like this, or maybe a part of that, one direction of it. So one direction is, I'd say, more straightforward than the other. But another hint is that to derive this, it's important to use the fact that f is closed and convex. In other words, it's important to use f star star being equal to f. So one direction is straightforward. For the other direction, you actually just say by symmetry, I get the reverse implication because of this property, f star star equals f. Okay, so if it's not in the homework, then I would practice it, because this is not like a bad, midterm question. And another property is that, for example, like well, actually a little different than subgradients, but conjugates are additive across blocks of variables. So if I have f1 of a block of variables u and f2 of a block of variables v, and I form the sum to define another function f of uv, then the conjugate decomposes as well. This comes right from the definition. So these are some useful properties of conjugates. Let's go through some examples before we start to talk about why we're interested in conjugates, just so we can get a firm grasp of what they are. Let's look at a simple quadratic function. So we're going to take f of x to be 1/2 x transpose qx, where q is positive definite. And let's form the conjugate function. So this is the maximum over all x of y transpose x minus 1/2 x transpose qx, which I can also think of, if I'd like. I mean, I don't need to write this next line, but maybe it's easier since we've dealt mostly with minimization problems in quadratics, as minus the minimum over all x of 1/2 x transpose qx minus x transpose y. And I know how to minimize a convex quadratic. Right? We've had lots of practice with that. For example, I could just take the derivative and set it equal to 0, or the gradient and set it equal to 0. So once I do that, I get, if I set 0 equal to the gradient of this, I get qx minus y. Right? I'm taking the gradient of this expression with respect to x and set it equal to 0 to derive the minimum. In other words, I get that x must be equal to q inverse times y. And that means that if I plug in for that value of x, I get that the conjugate function is simply equal to, you can see, ends up being 1/2 y transpose q inverse times y. Okay, we can, for example, we can look here. We get a whole y transpose q inverse times y, and we get minus 1/2 here. So the result ends up just being 1/2 y transpose q inverse times y. So there we derived the conjugate function. Yeah?
I think that's a typo in your slides, because you said y equals q inverse x.
Yeah, thank you. So ignore this. You could say maximize at x equals q inverse y. Thanks for pointing that out. OK, so what we saw was that the conjugate of a quadratic function was another quadratic function. That was just a quadratic function defined in terms of the inverse. So it's kind of like the inverse quadratic form. What do we get from Fenchel's inequality? Here's actually a pretty interesting fact. What does Fenchel's inequality tell us now? It tells us that the following bound is true. If I take x transpose y, that's less than or equal to 1/2 x transpose qx plus 1/2 y transpose q inverse y for any points x and y. Pretty interesting, pretty non-trivial inequality. You know, I don't think that this is something that you typically learn in, say, a linear algebra class, but it was trivial to prove this from the definition of a conjugate, Fenchel's inequality. It was one line, and it's just this, right? And then we derived the conjugate for quadratic, and here we got this kind of, I think, pretty non-trivial inequality here. So an interesting observation. So when I write, so positive definite in our language means symmetric and has the smallest eigenvalue bigger than 0. And positive semi-definite means symmetric and smallest eigenvalue bigger than or equal to 0. OK, let's go through a few more examples. How about if we look at an indicator function? So I just want to look at the indicator function of a set C. Right? Its conjugate function is, well, it's kind of trivial in a sense to write down. If I have f of x equal the indicator of x being in the set C, and I write down what f star of y is, it's just the maximum over all x of y transpose x minus the indicator function. And this is going to be infinite when x is outside the set and 0 otherwise. So this is nothing more than the maximum, the biggest I can make this inner product with x being in the set C. Okay, that's called the support function of the set C. Something maybe we haven't seen so far, but it's something that comes up a lot in, say, convex geometry, called the support function of the set C. It's the biggest I can make the inner product of y with any point x in the set C. Going to also be important. It's going to be important when we discuss cones, also at the end of this lecture. Okay. So here's now a property that we get right from this last property. Yeah. So how about norms? An interesting case. What happens if I take the conjugate of a norm? So I claim on the slide that if you give me a norm, its conjugate is the indicator function of its dual norm ball. So it's going to be 0 if I'm looking at a point y that has dual norm less than or equal to 1, and infinite otherwise. So it's going to be another really useful property, that the conjugate of a norm is the indicator of its dual norm ball, the unit ball in its dual norm. And one of the homework questions is to derive this fact. That I do remember, for sure. You can do it in a few ways. You can do it right from the definition. So you can go back to the definition of a conjugate here and ask yourself, what happens if I pass in here a y that has dual norm at most 1 and prove that the max is 0? And then you could say, what happens if I give myself a y that has dual norm bigger than 1 and prove that the max is infinity? And if you go through those two cases, you've just established this relationship. Here's an easier way to prove it. Just write down the high-level facts. So let's use the fact that f star star is equal to f for closed convex functions f. Now, if C is a closed convex set, then the indicator is a closed convex function. And the reverse of this property is true. In other words, the conjugate of the support function is the indicator function. So that means the conjugate of the support function is the indicator function. And apply that fact to norms. What is the norm? It's nothing else, in fact, than a norm is nothing else, in fact, than the support function of its dual norm ball. Right? Or said in terms of the dual norm is defined by the support function of its norm ball. Okay, so once I realize that, I can prove this property about norms without having to really do any mathematics, just by citing the facts that we saw here. So this sequence of scribbles would not be good enough to say verbatim on the homework, but fleshing that out would be a fine solution. Okay, any questions about conjugates? Okay, let's take a quick break, and then as soon as we come back, we're going to relate these to duality, so you'll see why we've been discussing them.